Hello there, my name's Nigel Bayliss. I'm a product manager in the Data Warehouse and Big Data Technologies Group. Here today to talk to you about automation in performance management. I think for that topic, we need to get some scope and context. So let's have a look. Oracle's autonomous database has automation built throughout. So for example, in infrastructure, you have Oracle Exadata. Then you have automation built into data center operations. So that's things like backup and recovery, DR. Now, the area I'm going to talk about is inside Oracle's cloud native database itself. So that's performance management inside the database. That means we want to automate the tuning of all physical data structures. So the overriding scope of this technology is to tune the way that we access data inside the database and optimize that. I'll be specific about the structures in a minute. The key point is that the automation is designed to reproduce the actions of skilled performance engineers. So in other words, we're building on Oracle's decades of heritage and best practice in order to build that into the way automation works and delivering those performance improvements to you without any kind of manual effort. So let's have a look at the database structures I mean. So we have things like indexing and partitioning, which I'm sure you're familiar with. And then we have materialized views and zone maps, which I'll talk about in a minute. So indexing. Indexing is there because it optimizes row access. So you very often see it in things like transaction processing systems that very often need to access a small amount of data or a small number of rows very quickly. Partitioning, obviously very commonly deployed, is amongst other things, it optimizes things like data scans. So in other words, if you have queries that need to theoretically trawl a lot of data, you can actually optimize the amount of data you need to scan. So typically things like date range queries, you avoid the need to scan an entire table, and instead you can scan a smaller region, a partition, for example. Materialized views, you're probably slightly less familiar with, but those are a way of pre-aggregating data. So you see these very much in very large databases where you have large queries that scan a lot of data and then aggregate the results. So you have group bys, counts, averages, those kind of things. So it's all about summarization and aggregation, but we do that in advance. And those aggregations and summaries are pre-materialized in the views. So the views are created, they contain this aggregated data, for example. And the key trick with materialized views is the application does not need to know they exist. So much like indexing and partitioning, it's all transparent in the application itself. So the trick Oracle pulls is that when the application issues a query against the base tables, it doesn't know there's this aggregation going on around the edges, but Oracle can rewrite the queries internally and use that pre-aggregated data. Zone maps, somewhat similar to partitioning in the way that they can reduce the amount of data you need to scan. So the way zone maps work is that if we know that the data is clustered in any way, so there are regions of data that's related, we can in fact use zone maps to optimize what regions of storage need to be physically scanned. So again, they're really about reducing the amount of data that needs to be trawled through in the database to get the answers to the query. All of these features can deliver significant performance improvements. So if they're used correctly, you can really transform the performance of an application. And perhaps more importantly, you can improve the scalability of the application. So for example, as data volumes grow, you are able, with these features, to maintain the performance and decouple the performance and the ability of the application to scope from the amount of data that's stored within it. So that's again a key requirement of many applications, that the performance is maintained even as the volumes of data grow, 5, 10, 100-fold or whatever. So let's take a closer look of what I mean by automation. As I've implied already, we want to remove the manual overhead of maintaining the system and maintain it with optimum performance. Very often, this requires a lot of effort to do in the real world. And that's generally because applications are not static. Data is not static, data changes. The physical structure of the database, in fact, might change over time as well. The requirements of the business change over time. So it's very rare to have a kind of performance tuning exercise to be a one-shot operation that's done at the beginning and then it's left and then that's it for all time. That rarely happens. So it's a key requirement, in fact, of any tuning task like this is that it's continuous, that it happens all the time. It takes into account what's happening with the database now and then makes allowances for that. So that means the side effect of that is that it can be without automation, it'll be a manual process that can continue throughout the life of the application. And generally speaking, a high level of skill is required. And it needs to, as I say, take account of change. So automation must transparently increase the performance of your database. And it does this by creating and maintaining these data structures that we've talked about. And the process of doing that really is about, first of all, analyzing the database workload. We need to understand the workload of the application, look at what it's physically doing. We, of course, need to know what the database schema is. That's a given, really. But also we need to know more subtle things like how is the data distributed? Where is it on storage? How is it placed? Those kind of things are in the data dictionary, but of course it takes a considerable amount of skill to understand that. Once we've performed that analysis, we do need a way of verifying that any candidate change that we might have does actually benefit the application. So this is very, very key. So the point I want to make is that the automation is not based on just theory. We look at the database, make decisions, but we check those. So in other words, we don't just sort of assume that X or Y is going to make things better. We actually need to check that those things make the database better. So the next step is a recommend phase. Now this is internal. I'll show you that in a minute. So the recommend phase is not necessarily something we need to look at. It's, if you like, an internal tick box. That's something that we can internally say, the database recommends X or Y or Z, and it's something you can look at later. But is the key step really is implement. So in other words, once we've verified that particular changes are good changes, and we know that if they're implemented, the application will benefit, we want to go ahead and implement them. So the key thing here to realize is that the automation is not just an advisor. It doesn't just sort of come up with ideas about how to make things better. It actually analyzes what's going on. It verifies those changes and it implements. So in other words, the database itself owns these changes. It's not some kind of theoretical process that you then deliver to a developer or database administrator to think about. It's all about owning the change we're going to make, because I think, again, a lot of you are probably aware that Oracle has had advisors for a long time. So in fact, there are advisors that Oracle has that you can use that will make recommendations about what you could do to the database, but they don't own the change. They don't actually physically implement those things. That's always the responsibility of a human to deal with down the line. Whereas what we want to do is also remove that step. So it makes the changes for you, and it makes that transparently. The changes are happening behind the scenes just to improve the performance of the application. I'll talk a little bit more about how that happens in a minute. So it's useful to view this as a cycle, and that reflects what I said earlier, that this is continuous. This is not something that's just done once and once alone. We have to always look at what's happening on the database and understand what's happening. So conceptually, you can imagine that in the middle, you have an automation engine. So this is, in fact, it's a series of engines or expert systems that can analyze the workloads, propose database structures, and ultimately implement them. So driving this cycle is this sort of central automation that we have. The starting point is at the top. So you have capture. Now, Oracle's done this for a long time, and this is one of the things I've always loved about Oracle. You kind of have features that we've built in over time, and then we can build on those and build on them and build on them. And so this is definitely an area where that's happened. So we've always, for years, we've collected things like workload usage information. So we know what objects are accessed, how they're accessed. We know that there are queries that are looking at these columns and those columns. We know that information. Of course, the data dictionary, by definition, knows the characteristics of those objects, but it also knows how big they are, how many rows are in there, and all those kind of good things. So we have a massive amount of information just waiting to be used in the data dictionary. We've had that there for a long time. So now we can make more use of that. So that's in the analysis phase, if you like. So we have all this information that's stored in the data dictionary, and we run an analysis. So the engine, if you like, in the middle is identifying candidate changes to the physical database schema. So think of those as candidates. It basically thinks this change and this change, or this series of changes, are going to be a benefit. But of course, we don't know that for sure yet. So that's where the verification comes in. So what we need to do is verify that these proposed candidate changes are going to actually improve performance. How on earth do we do that? Well, Oracle, again, for a long time has had the ability to run at the back end, if you like, queries. It can test, execute queries that are being used by the application. So that's exactly what we do. The database essentially remembers the queries. It remembers the workload that the application or applications use. And it can test those queries against proposed changes. And that means we can compare actual performance. So in other words, we can compare actual performance with or without these proposed changes. There's also a trick in which we can hide that from the workload. So in other words, this is something we can do without the workload seeing these changes in advance. So to summarize, what we're doing is we are looking at what objects we might want to create. We can actually create those and keep them hidden from the workload until we have verified that those objects do actually add benefit. So to do this, depending on the type of structure we're using, we can use things like make them invisible. So they are there, but the workload cannot see them. So you might be aware, for example, indexes can be built so they remain invisible. So that's one of the things that we do. We can create an index visible, yet workload cannot see it, but using database settings, we can allow our test workload to see them, to actually see these invisible objects. It can be told to see them. So that's again a key concept here, that we have the ability to test workload queries on changes that have been made but are still not visible to the workload until the verification is completed. I'm going to skip recommend for now. I'll come back to that because, as I mentioned, that's kind of like an internal step, right? We're just feeding through recommend. We want to own it, so we're going to go ahead and implement the changes. These changes are made online, so in other words, they happen transparently. They are transparent to the application. The application doesn't need to stop. So this is something that is essentially added over time, and we do those any operations that we do are basically online operations. The net result of the cycle, the entire cycle, is that we have an optimized physical database schema, and you have that without any user intervention. So how is this invoked? What's going on here, if you like, to make this all happen? So really, there's two modes of operation. You have continuous. And what I mean by that is that essentially what we do is we have the engine can wake up periodically. So it's always looking. So it wakes up, checks, goes to sleep again, wakes up, checks, and goes to sleep. So you have this sort of continuous process. So it's always going around the loop, happening 24/7, for example. And depending on the particular automation we're using, we also have the option to invoke this in an ad hoc manner. So in other words, we can, if we want, ask the question, can you tell me about X or Y now? Or can you tell me and implement in one go? And this can all happen on a production database, of course, because as I said, it's hidden. Other possibilities are running, for example, ad hoc on a production clone. The choice is going to be driven by a number of things. It depends on the physical database structure we're talking about here. Or are we talking about partitioning, or are we talking about indexing? So there is some dependency on what you would pick, what method you would pick for the different database structures. Also depends on things like resource availability. You may want to just offline all of this, keep it away from production. And it depends on things like time constraints. Maybe you want to perform this analysis in advance of a particular point in time. So things like that also will drive your decision about when and how you will want to invoke the automation itself. Bit of detail for you, for those of you that do like detail. The pattern between the different features is pretty consistent. So in other words, once you've seen one, you've seen them all. So you should be able to recognize the kind of pattern that we're following. So very often you're going to see it driven by configure. So configure is like the key way in. And actually, I want to mention at this point that these features being automated means that we don't want to have a lot of complex configuration. So one of the key things that I would say is you're not going to expect lots of little dials and tuning things to alter like you would often expect with some Oracle features. The purpose of this is to just work and to keep configuration down to a bare minimum. So you will see that if you look at the API documentation, you're going to see there's just a small number of things that are configurable, and that's done very much intentionally. So I think if you're a long-term database administrator, for example, that might come as a shock because, Oracle is often gives you loads of little tweaks and things that you can alter, whereas very much a design decision here is to keep the level of complexity right down to a minimum. So things are, ideally, we'd almost want an on-off switch and nothing else and nothing more. That's kind of the ideal that we want. But of course, there are certain things that you will need sometimes that you want to specify. But basically, configuration is down to a minimum. So for auto indexing, setting implement means that you've got this continuous invocation. It runs in the background and continuously will check to see whether index changes are deemed beneficial. If you really want, you can look at the task status. So you can go in and have a look when the task has run, for example. Here's an example with automatic partitioning where we are recommending a partition method. In fact, it's a little bit more than that, really. You can, in fact, recommend all the way through and it will create the partitions for you. In this case, we're using it in more of a mode where we're running on a clone. We're saying, can you tell me what partitioning works for our application? It goes away and checks that, does the verification step. And then ultimately, we've got DDL, which you can extract from the clone and then take that to your production environment and let it build the partition table for you, again, online. So what about reporting? Now, really reporting, I guess conceptually, again, you can see it is part of the recommend phase, if you like. Now, it's not, I see recommend as really an internal path. So in other words, it's something that the implement phase knows about. The database administrator or developer doesn't need to know particularly what the recommend is, but if you want to look, it is there. Essentially what we do is that the engine in the middle is always recording what happens, So there is transparency there. It does report everything it does, and that is held inside the data dictionary. And the good part of that is that you can generate the report anytime. So later down the line, you can look at the reports and see what happened when, if you want to. So there is a transparency there. So you may use it, for example, to get proof points. If you're capacity planning, it will tell you the difference in performance of your queries individually if you want. So you can get a very fine level of detail if you want it. But the numbers are there if you want to look at it. Yeah, there's no particular need to do that, but as I say, it is there. So again, you have the potential, in fact, to use a report-only mode. So if you want to, you can actually say, just check all of this out, and then I'll have a look at it, and then I'll choose to implement it later on. So that model is also supported. Very easy to use. You just say you want it running in a report-only mode, and then the reports look like this, really. You just call the API, report last activity, for example. There's date ranges as well you can use, of course. So you can just say what happened most recently, and then you will get a report generated. It's pretty straightforward. If you've used things like SQL Tuning Advisor or what have you, the report format's going to be very familiar. You'll just recognize it straight away. So you're going to be able to see things like the queries that were tested, because remember, we are testing workload queries, so we can actually full transparency see what queries were actually looked at by the whole verification step, and it will tell you what the before and after performance was. In other words, the performance before the change or without the change, and the performance with the change. So you can see that very specifically. Of course, the purpose again is for the automation to look at this, parse this information, then make decisions about what to do itself. So again, there's no particular reason for you to have to go and understand the reports and pick through them or what have you, but they're quite interesting to look at, of course. They are nice if you're a detail person. You'll see things like the performance of the query before and after. You'll see things like the execution plans before and after, that kind of thing. So it's very rich in terms of detail, but as I mentioned, you don't have to look. But those of you that like to look, it is there. So let's look at some of the proof points. Now, this obviously our internal testing as we get results from that. So we're looking at here the NetSuite ERP application. So this is a very transactional system, and you can kind of see that from the workload characteristics. You're looking at a huge number of SQL statements, lots of tables, a large number of indexes that were created by hand based on expert knowledge. So what we did for this test is to drop all the secondary indexes, things like that are not primary key or foreign key, and then let the engine figure out what indexes are going to be useful to the workload. So we essentially let the workload go, leave it running, and what's nice about this is you kind of just leave it alone. It just works by itself, of course. That's again the whole purpose. So we let auto indexing work, and then implement, and then we took a look. So it's kind of like that. So the key things to notice, if you look at the chart on the right hand side, what this is showing is that we had an elapsed time of 1172 seconds, and versus for a particular test workload with the hand tune indexes, and then we're comparing that with the auto indexes. So you see the performance is pretty comparable. But the thing that is particularly interesting is the number of indexes has reduced quite significantly with auto indexing. And in fact, you can see this at work. What's interesting about seeing the sort of the mind of the machine is it's very good at optimizing the indexes that it creates. So what I mean by that is what you generally see from an expert tuner quite often is that indexes are generally like one or two columns. So the indexes are sort of created. I would call that sort of a conservative approach, where indexes are created on individual columns. whereas automatic indexing is a bit somewhat smarter at combining together indexed columns where it adds benefit. It's very good at that. So the net result tends to be a higher proportion of maybe 2 column indexes than a manual approach, and fewer indexes overall. So it's quite interesting how it does it. So yeah, so the net result is you get fewer indexes, but the performance is good, and you don't need that manual skill to figure out what hand-tuned indexes to add. So if we look at now automatic materialized views, a similar kind of presentation is that we have fewer queries, as you'd expect, because this is more of a data warehousing style workload. So lots of a smaller number of large queries, smaller number of tables, and largest table is 3.2 billion rows. And we recommended, well, the automation recommended three materialized views. You said 2 there, 3 materialized views. And doesn't sound like a lot, but that's the thing about materialized views, is they get, if you're smart, particularly if you're smart about which ones you create, they can affect a large number of queries, relatively speaking. So in this case, you have 3 materialized views running, improving 16 queries overall. So what did that do to the workload? You reduced the sort of overall end-to-end time of the full 77 queries by about 23%. You'll see in this chart here, this is comparing the performance of the queries that benefited from the materialized views. So of course, this is again where what I was talking about earlier, that the performance benefits can be massive. So we've got here, if you like, before runtime versus the after runtime. So we got very large improvements, down from 106 seconds to 19 seconds or so for the 16 queries that we improved. So of course, those all went massively more quickly, and then the overall end-to-end time was effective at about 23%, something like that. So yeah, so the trick with materialized views is to select a small number that can serve a large number of queries. That can be quite difficult to do, but we've built that into the automation, so it's pretty nice. So in summary, we have an expert system or a series of systems that maintain database structures and reproduce what a skilled performance engineer would be expected to do. Remember that the candidate structure changes. The things that we're adding are validated before they are implemented, and they're validated offline. The entire process is fully automatic. It is transparent, it is continuous, and it does not require any manual intervention at all from database administrators or developers, for example. Okay. So for more information, you'll see this topic covered in, for example, the Autonomous Database blog, the Optimizer blog. There is a hands-on lab for automatic indexing, and it's always worth, of course, checking out the Autonomous Database documentation as well. Okay, so all that remains for me to say is thank you for listening. I hope you enjoyed the topic, and I'll see you soon, no doubt. Thank you, bye-bye.